a language model has two very distinct kinds of compute that you do. One is you're gonna have this big input that just represents a query that you're putting into the input field, and in one gulp of the model, you're going to try to compute all of that. So we call that the encode problem, and that really ends up being very compute limiting. The real problem is the generation or the decode problem. The key point is every single one of those tokens that you generate, you've had to pass through the entire model once. So immediately you would say, well, we have to then have parity with bandwidth and compute power. But the reality is the physics of all of this is such that no system generally is like that.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I am your host, Sam Charrington. And today I'm joined by Chris Lott. Chris is a Senior Director of Engineering with Qualcomm AI Research. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Chris, welcome to the podcast.
Thanks, Sam. Very happy to be here.
I'm excited for our conversation. We are going to be doing what I think will be a bit of a deep dive into efficient large language models on the edge. Before we dive into the topic, I'd love to have you share a little bit about your background and how you came to work on all this stuff.
Okay. I started out actually working on test instrumentation and then early days of GPS. So my background, communication signal processing, but then I got into control theory and then went and did a PhD in control, and specifically stochastic control, which has a lot of commonality with what we call AI and ML now. So then I joined Qualcomm, and in the early part, I did system design and standardization of wireless, of all the wireless systems, and that led to all these voice systems and then high-speed cellular data that did it up into through LTE. And then as Qualcomm developed, we went beyond modem and we became an SoC company, which means we start adding more and more integration of all the different functionalities that you might want on your phone, on your tablet, into one chip. And then that brings in a lot of compute aspects, GPU, CPU, and then we started adding accelerators for AI. And then this led to, I guess, getting into the whole AI field for those of us who had the right kind of background and the right interest. And so that's where I've been in, the last probably 8 years.
And your focus is on the engineering side within research. So is that primarily working with productization of innovations on the research side?
So our group is called AI Research, Qualcomm AI Research. But we are organized we want our research to be basically there's two poles and then a lot in between. So one pole is contributing to the research community, focused on papers and the frontiers at that level. And then there's what we call system engineering, which is integrating, basically doing design and being the main system design and support group for AI in the company. And then, but we actually are organized in a way we want our AI researchers to also be part of system engineering at different levels. So everyone has some aspects of both, but my focus has been more on the system engineering, partly because of my system design background, but also that's where a lot of our action is right now. We're going through this period where AI models, we're getting to the rubber hits the road aspect of where they're useful, how do we make them efficient, and how do we actually integrate them into full designed systems.
That's maybe a good segue to talking about LLMs on the edge and why you see that as being so important, relative to using them via APIs on the cloud.
No, exactly, and that's a big discussion and this topic that'll be going on for a while. But there's a number of reasons we think supporting LLMs on the edge is the future, and it's because partly because we have the compute and bandwidth and just storage aspects that we can do a lot on the edge. We have that capability, and it just makes economic sense to use it where it's feasible. But also, the edge is also a place where there's a lot of unique, information and personal data, et cetera, that can be used to improve how the LLM is used. So obvious examples are camera, audio, sensors, and just awareness of, the phone indicates something about your situation. And you can use that information um, to help when you say, "Oh, what is this? Where am I?" or any question you might pose. You can use the sort of contextual information that is only growing over time.
So primarily situation and personalization aspects.
Yeah. So some of it. So I was going to say it also can extend over time. Something that it would learn from you as you are using the device. Okay. And then, it's certainly feasible to store all this on device in a very private way in your own database that can then be accessed while you're, trying to achieve different tasks. So yeah, it can learn your preferences, your habits, and just the typical things that have happened in the past that often are a best indication of what you're looking for now.
You mentioned uh, storing that type of preference information in local databases. Um, what's the relationship between databases and models with regards to personalization and preference and intent type of information?
So you might view this as a form of RAG, which is just instead of having the model have to store everything, you're actually storing information that it can then retrieve when it needs to. And so, I mean, there's definitely one major trend, which is just the standard database, non-SQL, SQLite kind of things that are very readily supported on a mobile device. And then the system simply is deciding what aspects of your daily life to store. And this could be your recent emails, your recent chats, discussions, and or just other aspects of your behavior, your calendar, of course. And all of these things can be made available for an agent that's on the device that's trying to anticipate. It can try to anticipate what you need, or simply retrieve things that may be hard for you to remember. But as simple as, oh, you have this thing coming up in your calendar. But also far more, obviously, far more. What new LM technology lets us do is do all of that far more deeply.
And so you mentioned the kind of this personalization and situation opportunity. Um, but I'm also imagining, and you also mentioned kind of the availability of the local resource, compute and the like. I've got to imagine latency is a big part of the attraction of using the device. I'm thinking of my own experiences using like OpenAI advanced voice mode. Like it's amazing, but it also, there are some glitches that at least I experience frequently that seem like they have to do with latency. Like the prematurely stopping the a generation or listening. And it seems like if we could tighten that loop, we'd be the performance and the experience would be better.
It depends on what you're trying to do and what the model is, because there is a limit on what we can support and how long it takes to run on the local device, and whether we can do the task that you're needing right now. But our goal definitely. So this brings up this whole question, and this is one of our great questions now. How much can we pack into the smaller language models? And how efficiently can we have them run with these databases and things where the model doesn't have to store everything itself? It just has to be an effective agent and communicator, right? And but if but and then and how are the resources on the device being used to efficiently be able to respond? So we size everything. So yes, to minimize that latency, and that is what we are working on. Also, is new developments in hardware, new developments in software, and also algorithmic things that I can also describe on how we do improve that efficiency. But yes, the goal is literally you have this device in front of you that is capable of just immediately understanding you and responding with minimal latency.
Hmm. And via voice, not just text.
Oh yeah, and this, in fact, if you know what one of our main, I'll say, pitches right now is that this is all going to lead to voice UI, which is literally, and if you want the very high level simple scheme, anything that you are currently doing on your phone right now you actually will be able to do instead of clicking or touching or controlling it with your hand. For at each, say you're going to an app or a web page and having to click through and figure things out, it will learn how to do things, and also that you'll be able to give high level commands in voice and say, "Oh, please just go do blank," and something that it has learned to do or already knows how to do. And that literally running apps on the phone, this becomes how you do it in the long run.
Yeah, I was at the Snapdragon Summit when Cristiano was talking about this idea, vision, and while there are a lot of gaps that need to be filled in order to get there, like the idea that part of what a quote unquote agent on your device is doing is masking or abstracting away a lot of complexity, both, hardware and software and settings and all these things that exist on our devices and making them easily accessible via, voice, natural language voice commands, I think is a compelling one because these devices can do so much.
Yeah, and they clutter our mind having to remember how to do this and that, whereas we know we just want to do blank and we don't want to have to remember all this stuff. Yeah, Cristiano, our CEO, his I remember his statement is something like, "We want to break the paradigm of the app construct," or something like that. But it is this exactly. But it really just plays into an age-old dream of AI agents, AI just being able to have enough understanding of everything that it really just becomes this useful little assistant to you.
So, of course, we're here to dig into the details. And I think maybe a place to start there is to really narrow in on the device constraints and where the way we need to use the devices to work with LLMs bump up against those constraints.
Yeah, so let me mention. So one of the first things we did, um, as as this whole generative AI field has been effectively exploding, is how far can we push things on our devices? We've been working on AI for a while, but large LLMs are a new kind of. They have very specific properties, and they stress the hardware and software in unique ways. And so, just I do think a good example is when we said, okay, we're going to put the Llama 7 billion model on a smartphone and a little while ago now, but that was our first say, okay, what does it take to do this, and what are the limiting factors? So I'll just mention a language model has two very distinct kinds of compute that you do. One is you're gonna have this big input. It might be thousands, hundreds, thousands of tokens. It just represents a query. It could also represent data in context learning that you're putting into the input field. And in one gulp of the model, you're going to try to compute all of that. So we call that the encode problem. And that really ends up being very compute limiting for almost any kind of hardware. and and so, but we've put enough compute power uh, in our edge devices that they are able to do this pretty efficiently. And I could give numbers at some point, but like, yeah, you can do. We look at like 4,000 input size fields, and we do it in a couple seconds, something like that, and that's already quite powerful, actually. But then we realize the real problem is the generation or the decode problem of LLMs, which is they're autoregressive in the sense that what they do is they take all those inputs that have been encoded, and then they say, okay, then it just starts generating one token. And here, token really can just think of as a word, right? One word at a time. And goes, okay, generate the next word. Okay, now that's the context. That's the history. Now generate the next word. And you do that one word at a time. And then the key point is every single one of those tokens that you generate, you've gone through the entire model. You've had to pass through the entire model once. Okay. And in fact, in our computer architecture circles, they have a parameter they call the intensity, which really is every time you read something from the memory, how much compute do you do with it? And it gives you some sense of the balance of how the bandwidth is supporting the compute. Maybe I'll just contrast with in the old convolutional network days, every weight that you read from the model was used, dozens, hundreds of times, something. And that just made it that's usually what leads to being compute bound, the way things are sized. But with transformer decoders, they literally have an intensity of one, and it just means you do one mac, one multiply accumulate for every weight that you read in over the bandwidth. Now, and so immediately you would say, well, okay, we have to then have parity with bandwidth and compute power to make that balance. But the reality is, the physics of all of this is such that no system generally is like that, because moving data takes energy, and and takes it takes a certain amount of time. And basically, bandwidths are some orders of magnitude lower than the compute power on many devices, most devices, I would say.
So we're talking about DRAM bandwidth here. This is things like DDR3, 6500, that kind of thing.
These models are so big that you don't put them on like the local memory that might be local to the processor itself. You will have like a local, we call it the TCM, the tightly coupled memory to the processor itself. Okay, but that memory tends to be measured in the megabytes, maybe even single digit or double digit megabytes. But we're talking about models that take gigabytes. And so it's only cost effective at all to do that in DRAM. So then, yes. So then, and that is the whole fundamental crux of token generation, which is we're going to generate one token at a time. We have to read gigabytes of memory into the processing for that purpose. And that's going to happen over the DDR bandwidth. Yeah. So, and then you're absolutely right. There's these standards for the memory controllers that support various bandwidths, and just I think maybe we're saying we're currently in what we call LP5. Okay, and sorry, yeah, we're currently in LP5, and in the future we'll be moving to LP6. And but the kind of deltas you get in bandwidth currently our processors are supporting 50, 60, 70 gigabytes per second. Okay, and in the future that'll go to like 113 is what I understand. That's what LP6 will give. That's quite, it's almost factor of 2. That's nice. But it's still, we're still heavily bandwidth limited. It's nowhere near what the processors could support just from a compute point of view.
You talked about the difference between encoding and decoding, and encoding is compute intensive and decoding is bandwidth limited. How do those limitations translate into LLM metrics that people care about?
So when talking about encode, I'll just bring up what is the most standard one, which is called time to first token. And it literally is the time, as I was mentioning in the encode problem, maybe you'll do 4,000 tokens all at once. You can do that in one pass of the model if you have the right structure. So it all comes down to how fast you can compute for like a 4K input. And then when you're done, then as soon as you finish that, you're going to generate your first token of output. So if you're the user, you may have asked a question, and then it may have pulled in some external information, put that into the input to the LLM, and the LLM will process all that, use that, and then start generating the output. So that the time it took from you to ask your question to when that first token appears, we call time to first token. But once the first token appears and then things start being generated, your output response generated, then it's that time of we call that tokens per second. Of course, it's just the amount of time it took for. So the output might take a few hundred tokens. That would be typical for some kind of response, or it might be something even longer. And then tokens per second is that metric. There are other very important metrics for the edge. In fact, they might be somewhat unique to edge devices because these devices are mobile often, and they have their own power source at least some of the time. And you may realize in smartphone design, it's like battery life is like one of the most fundamental things that people care about. Just power, how much power you're using, and so
So I'm
we also have
imagining you're going to say something like tokens per watt or something.
right, actually tokens per joule, if you know, because the point is, you could watts is joules per second, so you're using up some power while you're outputting. So it's really the relative rate of those that tell you, like, really the point is how much energy. Joule isn't a unit of energy. How much energy did you use to output 100 tokens? Is how much you sucked from the battery. You can think of the battery as storing joules, and then each token takes up some joules from the battery. You could do that in milliamp hours, by the way, if you want a different unit. But that we actually do things in tokens per joule or tokens per picojoule, or however you want to do it.
Given the constraints, like a big part of what you're doing from a research perspective is trying to optimize around those constraints. What are some of the kind of foundational ways that you think about delivering LLMs on the edge in light of those constraints?
Yeah, I'll make one more thing that was not even on my radar at the beginning, but is very much what we all think about now. Um, the other big economic issue with smartphones, tablets, etc., is how much DRAM you can put into them, and it's pretty much purely a cost question, but it's a very non-trivial one. And the typical phone these days, I believe, 4 GB, many have 8 GB. That's about the typical range. Um, and then what's interesting, like consider LLMs that we want to support. You need a certain size LLM to just start having some of the real, impressive power that they can show. And at some point we thought maybe
Power in
seven
terms of capability, not in terms of
capability. I'm sorry, yeah, just
yeah.
the impressive performance they're giving on applications, right?
Right, right.
And in fact, that's why we said, look, we have to at least try Llama 7 billion and see if we can do that. Okay, on a little smartphone, and you can. But if you want to know what the primary issue more than anything else, it turns out it's not even token rate or any of those things. The primary issue is the footprint in the DRAM.
So just being able to fit the model in the
Yeah,
RAM so you can even think about running it.
that's right. That's right. And interestingly, and I'll mention all of these devices, pretty much probably every computer will have a concept of this sort of fast access DRAM and then a kind of drive like a flash drive, solid state, something where it's storing things more permanently. We do have more things you can store on you can store larger things on the flash drive. Okay. But to run a model, as I'm saying, every time you generate a token, you have to use the entire model during generation. And that means pretty much that means you have to have it in DRAM. And okay, so it may not be in DRAM constantly, but it has to be able to be in DRAM. And the way phones work, the way all these systems work, there'll be some of the DRAM is always filled with the OS, like could be Android or iOS. And then part of the DRAM is running your persistent apps, which most people will have something that's just some sort of persistent app. Okay. And so it leaves you whatever is left in say 8 GB to run your LLM. Okay. All right. And then so then consider like a llama, literally that model has 7 billion parameters. So even if you encoded it one model parameter and 1 byte, so there's a whole thing here. I'll just mention briefly. All these models, when they're first developed, they're developed as floating point numbers, for simplicity and for training, etc. Um, it's really one of the great questions, and I really think there's a very interesting just whole set of things that we think about here. Or basically, what are the limits of computation to achieve comparable performance to what, say, the floating point version of a model is? Okay, and now this has been studied a long time in various guises, and the LLM context is bringing a lot of that in. But the main thing it comes down to: can we pare it down? Can we prune it? The model may be 7 billion parameters. Does it really need? It was trained that way, but does it need all those parameters? Can you prune it down? Or can you quantize those floating point numbers into smaller and smaller, numbers? How far can you go? And okay, so and still achieve good performance. So let me go back to saying, if a 7 billion model is in floating point, and even that would typically be FP16, if you know that term, that's 2 bytes per parameter. That's 14 gigabytes right there. Okay, all right. And even if it were, if you could go down to 1 byte, well, that's 8 gigabytes. All that is still way too large, or 7 or 8 gigabytes. Okay. So the first thing we do, and I'm sure this is something well known, but these LLMs, interestingly, generally you can take them down to 4 bits if you do quantization the right way. You can take the weights down to 4 bits. And that's an interesting thing. This is something very conceptually interesting about why and how the model is working properly, even under those conditions. But that is how it's done. That's like the most standard thing now, is to take these models, take them to 4 bits. And so a 7 billion parameter model can be taken, the model parameters down to about 3.5 gigabytes. That's at least feasible on a smartphone. And that's what our first demos, and that's all the things that we were first doing. And I can just mention on the side, quantization is its own long topic. We have whole teams that do a lot, and it's really something that our research group is very known for. But actually,
And I can include some links to conversations with some of the researchers about various quantization efforts in the show notes.
okay, yeah, perfect. And then like one of the trends now in quantization is, well, different parts of the model may quantize better than other parts, and we call this multi-precision. And some of it you could even take down to 2 bits, interestingly, but other parts actually do better at 8 bits, the overall performance. So just those are all the things that we're currently doing. And then one more thing I think is definitely a trend. We have efforts in this. Is how can we just, as I was mentioning, power tokens per joule is very important. All that's fundamentally how much energy you're burning reading the model to where it can be computed. And so it is, there is rethinking of architectures for that purpose, which is minimize data movement. And yeah, you get down to some really fundamental, the physics of moving data, computing, and doing the computations and storing them.
And what's an example of that?
So I'll just say what it really comes down to is, can you locate, can you minimize, can you really make the compute as coupled with the memory as you can? I mean, one example is beef up as you can the tightly coupled memory and see how far you can push that. But that's one example.
So you mentioned SLM, small language models, which is that fundamentally trying to address the limitation in DRAM size, or is it equally trying to address performance? Like, how do you think about where SLMs come in and why there's so much interest in those nowadays?
So it's definitely about the footprint, the DRAM size. But it is also about those other things, about the time to first story. But I whether those are those may not be as driving as the DRAM size, which is an interesting fact. Okay, maybe you can accept a little slower token rate under some conditions if you're going to get a better answer, but you can't have a bigger model under if you don't have the DRAM. Okay, and so yeah, so there's this I think a lot of great effort now on what we have come to call SLMs, and for me that the range of that is maybe 2 to 4, maybe up to 7 gigabytes. Sorry, billion parameter models. But what's turning out these days, what we see is there's this sweet spot that seems to be 3 to 4 billion parameters.
Is it a meaningful distinction to you talked a little bit about the effort to get the 7 billion parameter llama model running on a device? Presumably you started with a native 7 billion parameter model, and then there's um, a optimized smaller version of that. You can correct me in a second, but the real question I'm trying to get at is like, is when you talk about SLMs, is it a meaningful distinction to talk about like a smaller version of a larger, natively larger model, or like a architected to be small language model?
What's interesting? It is. I am speaking about the ones that were targeted for being small language models
Okay.
mostly.
Okay.
By the way, they might use larger models to distill some of the capability of the larger model during their training. So in that sense, you can view
In
them
that
as the
sense, it's
small.
not that interesting. Like it's a confusing distinction, maybe.
Well, but okay, but most of them, okay, if you know like the Phi models from Microsoft, isn't just pick those as an. And by the even these days, Llama has a 3 billion, right? Those, however they trained so it doesn't even really matter how they got there in some sense, right? And they will all they'll train from scratch in the pre-training part. Those giant, you know, Terra token training sets that we use, and then whether they can improve performance by distilling from a large model, or they often do what Microsoft does is these curriculum learning things, and they'll and synthetically generated data of very particular types, and they have all these methods, right, to try to see if you can pack more capability into these smaller models. So whether you do it that way or distilling or so whatever combination, that's not all that's not fundamental to the point that it comes down to what can we do with a model that is 3 billion parameters, because that's something that very readily can go on our devices right now, and then we try to figure out what we can do with what are the how far we can take that. And then the other, I think, really fascinating topic is, I sometimes view what's happening now is there's a kind of system engineering phase for all of this from in our terms, okay? And that's really to me what like compound AI is, or any of these things where, okay, this model is not going to be standalone; it's in a system design, and how do we do that? And then the trade offs are not even, well, I can't fit it, so I'm going to use the smaller model. Then the trade off is a model of this size is sufficient to perform this function in this larger system, and it runs faster and it's more efficient and it has less energy, and in fact it's better for this question answering that we're doing using RAG, where we're grabbing the data from outside anyway. And there maybe lots more. We know a lot of examples now of scanning a lot of the things going on the phone, processing it, coming up with summaries, or using that information from the past, where the smaller models are perfectly adequate and much more efficient.
When you think about small language models as a direction, like what are the areas that you're specifically working in? Creating new small language models, creating SLMs based on other people's LLMs, um, figuring out what, are there complementary system components that can make SLMs more viable? Like, how does that translate into practical research and engineering directions for you?
So maybe there's two main aspects. We do train our own SLMs, and we're studying the architectures, seeing what architectures are performing well, and also how they are mapping to our hardware. We do want the flexibility to try out things in that space. But we also are users of the public SLMs, or there are those from we do have sets of customers that bring in their own unique ones that we are supporting. But then we study this problem in uh, our orchestrator, which means how do we support an SLM in this sort of larger context of a system design, and the software that's using it, and the RAG system and the databases, and all the things that might be associated, and how is that all running on our devices. And in that context, what we also will fine tune existing models. We have our own models, we fine tune existing models, we have customer models. All of those things are happening.
In some ways, it's kind of a traditional Qualcomm play in the sense of like you've got this model type that's gaining popularity. How do we add a bunch of value by creating components around it that will let it do more things?
Yeah, actually, that's a good way to put it. We have this philosophy, and this is the system engineering side. We'll do end-to-end design, even if we are not the provider of all components in the end-to-end design. We use this analogy in the wireless system, which I had a lot of experience, which is we would do end-to-end mobile base station, drive around, and take all the data, support the standards, to write the standards often, and in the end, we our high volume is the mobile side chip, right? But we are also fully aware and developing the full end-to-end system design, and I think that is a good, you know if not analogy, just exact example of what we're doing here, which is the end-to-end design here is down to what is actually happening on the device, on the smartphone, on a daily basis, and all the components that we provide, how are they playing into it and doing it all efficiently? And the only way to really even plan our hardware software developments, we have to know what our future systems are going to look like.
You've emphasized thus far kind of the memory constraints and the bandwidth for generation. Are there things happening on the compute side as well? I've got to imagine, like, as you're trying to use longer and longer context windows, it's still important that you have efficient compute structures, right?
Oh, even yeah, that's where it really happens. Let me go back to the distinction between the encode and the generation decode part. Um, as I was saying, the encode part is very compute bound, which means the time it takes to first token is limited by what your compute power is, and that just becomes more and more so as the context window that basically the number of tokens you're computing increases. And there's this trend. I always refer to Google for their 1 million context length that they have been claiming for Gemini. And so the compute itself during encode is an n squared in the max, if you like, because every token attends to every other token. So number of tokens you're attending to, and then how many tokens that are attending, and that's an n squared. Um, so you can get to, and then people want to support. I was mentioning 4K. 4K is like the sweet spot of what we currently do on mobile devices, but that there are many that are saying we want to do 16K, we want to go to 128K. You can imagine how that grows, because then you can start doing significant things all in one process of an LLM, right? Summarize this entire novel. People use that example, right? So and then the n squared problem. I'll just say right now on our mobile device that'll just kill you at 128K. It could be a background task. I could even say, if you're willing to wait, it's possible. But okay, so what we do instead, though, is and then the flip side too is, once you have that long context, and now that you're generating tokens, that also slows down, because every new token is based on all the previous history. If that previous history is 128K, that's a lot of processing you have to do just to generate the next token. Okay. And then I should go back to the footprint DRAM question. So I'll introduce this term KV, which people may know. But the way transformers work is for every token in the past that you've processed, like the encoding problem is entirely take all the input tokens and create their KVs, which stands for key and value. Okay. And that may be enough here. So, but the thing is, you have to allocate that. That has to be stored also in memory as you're generating going forward. So that actually takes up DRAM. And right around, that starts mattering right around when the context window size is on the same order as what as the model size. If you want a interesting little rule of thumb. So like a Llama 7 model, Llama 8 model, the model size is 4K. That's the vector. That's the embedding size of the model, right? The token embedding size, and it's right around on that order, that context length, where these like the compute aspects and these DRAM aspects really start taking off and start dominating. Okay,
Hmm. And is
and
that
so
related to that intensity calculation that you mentioned?
actually for well, the intensity is still the same from a compute point of view, but this the number of it really what actually during generation, it's the bandwidth of reading in all those KVs is what's slowing you down. Usually, you're still not compute bound, you're still bandwidth bound, but you're having to read more and more. So you have to, I should maybe say it that way. You have to read the entire model, and you have to read the whole history of the KVs. Okay, for all the previous tokens, every time you generate a new token. And if those KVs are relatively small, when you start out, those can be relatively small. But if you have a longer history, it really interesting. It flips, and suddenly the KVs are everything. And for the truly long contexts, yeah. Okay, now that's in kind of the raw form, and that is what puts these limits on what are the practical context windows that we currently support. But we do have a very active effort, and we will have a paper coming out pretty soon on this topic, which is we call it KV compression, and because it's a very how much of those historical KVs do you actually have to store? And now the first thing is, as usual, there's a quantization question, and everybody realized you can basically go to 8 bits for KVs, but going to 4 bits doesn't always work. So if you don't know where these boundaries are, okay. But you can also, interestingly, you can drop some KVs, or they're not all important. Not all the previous historical, input words effectively have the same importance. You can imagine how you could compress that. Just doing it as a straight compression problem without any semantic context doesn't work. Okay, but if you have but you can compress them based on their relative importance, and we have ways. This is what the whole thing is. How do you estimate the relative importance of the historical inputs? And that even depends on what the task you're trying to achieve is. So, and people do other ways. Well,
Tasks like question answering
yeah. So if you're doing question
versus
answering, well, you can't lose the fact of what you have to answer the question.
right.
That's in one of the. But some of the tokens are the
Yeah,
right,
yeah.
and who knows, what really is needed. So, but actually, and so there's ways you can do it that's very semantically aware, or even context of, I should say, domain aware of what you're trying to do. But another approach, one of the things we've been doing is more generic, but just using the statistics of them and how they relate to each other to decide what you really need to store. And so what we'll typically, and if you want to know what a very practical, like on phone question is, as I say, you have this fixed DRAM, you have a fixed allocation you're gonna put for the model itself, and then you have a fixed allocation for how much KV you're going to support. Okay, because you have to have it available. And then you say, okay, but so how far a context? So a simple thing is, well, that KV can support a certain. We'll pick 8 bits for KVs, and we'll do a context window that fits that. Okay, that's fine. But you can also go beyond that, and then you have this compression problem. You're going to decide what you're going to fit into this fixed size that you have, and that's the interesting question that we've been working on for a while. And this is very practical. Like this is something very customers and people are already using these kinds of things.
And you mentioned that the using 8-bit KVs, like, is there any work to look at like variable length encodings for KVs? Is that an interesting area?
Yeah, absolutely. We definitely have done that also ourselves. There's always this trade-off in complexity versus how much it actually is worth it. We're totally into system engineering stuff, but it absolutely, in the same way that it's true for weights, yes, it also can apply to KVs. Actually, that is something that we even saw. Instead of you had this question of dropping an L token, or making it 2 bits, so there was something there, and exactly those all trade-offs exist.
So KV compression is an area you mentioned a little bit about. compute architectures to adapt the compute to the model. um, the converse of that is model architectures to adapt the model to the compute. I'm imagining that's an area of research as well.
Oh yeah, and that leads into something we track and consider even contributing more ourselves, which are the new architectures that are potentially replacing transformers, or at least replacing layers in transformers, such as state
Like
space
state space
models.
models.
Yeah, maybe the best example, and I think as often understood these days, um, hybrids of transformer layers and state space layers, like the Mamba 2s, et cetera, may end up being a real contender, because you can remove these KV growth problems and storage problems. You're effectively saying we're just going to, it's funny. I'll make this comparison. When we say we're going to fix the KV size, and we just have to do that. And yet the KVs in the vanilla transformer will keep growing. Well, we're going to compress. Well, that's something that's quite similar in a sense to what what a state space layer would do, which is they just fix the size. They say, here's the size, no matter what. We're going to a priori decide this is the size, and we're going to pack all the previous information that has happened at this layer into that one vector. And um, which fits perfectly the kind of constraints we actually do see, is what I'm trying to imply. And but the problem is, that doesn't always work well. It depends how far you can take that that pure design, and it's probably because, as things, if you're running longer and longer, more and more things happen. It's very hard to know exactly what you should have stored, and again, that's domain dependent. It's related to the KV compression problem of, depending on what you're doing, whether that really works or not is what we find. Okay. But there may the, but if you have some amount, the idea that you need a full KV for every layer in the model, which is how the basic transformer works, that's definitely something that could be questioned. And I didn't mention it before, but you could also, even this KV, when we say we're going to minimize, we're going to have a fixed KV size and we're going to have to compress it, that can also be a per layer decision. Or some layers may need less than other layers. And that actually ties directly then into what these state space models are also trying to do. And their method of compression, in many cases seems to work quite well. And but standalone, maybe not so much. You need that some layers need the long memory and some don't. So to us, it's a natural then development beyond this, our fixed KV size compression stuff, into bringing in other layers that just are inherently limited in how much memory you need. And let's see what combinations of that work best for a given problem domain. So I would say it's not like we're going to converge on a single architecture. It's going to depend on what use case is, and how much other resources you have.
Again, trying to map this onto, what you would do versus, um, what the customer would do. Like, presumably within some bounds, if I want to write a state space model and, run it on the hardware, it's just, it's gonna work. And what you're trying to do is make it work better.
So
So
I'll be
like,
very. You asked a question that we're always engaged with. Okay,
yeah.
which is, what is our best role? And so I mentioned we'll do the end-to-end system design, because that's how we understand everything and how it all fits. Okay. And so very much first thing is, we can then work with, we have some major customers, they're doing all sorts of things, some of the major phone vendors, et cetera. We help them effectively. We give them, we say, look, we did this is how well it worked, and that'll influence how they do their designs. But you're right, they'll own the model in the end. But for example, we'll just give them this example of, here's a state space model running on our hardware, here's a hybrid model, more likely. And then there's things that we think about that, only certain others would start at least thinking about, which is, do state space models quantize well? And when you're comparing state space and transformer or these different architectures, they generally won't start with that, but it's one of the primary questions for us. And the way they work, where the state is limited, it's a limited state size, and those and it's iterative, autoregressive. Inherently, it could have more quantization limitations than a transformer, than just storing KVs at a certain quantization level. That's just an example of what we will do. And so the truth is, in the end, we span this range of, we give reference designs, we do and then we provide the pieces that are fundamental to running things on our hardware. And we will give example of, uh, how we fine tuned this model in this way, and this how that fits, things like that.
Yeah, what I'm What's kind of coming to mind for me or becoming apparent as we kind of talk through these different ways of supporting LLMs in the edge is like almost a maturity model, like quantization and pruning. Like you guys have been doing that for years. I've been talking to you, your researchers about how that space has been evolving for years. And so, it's mature and there are primitives baked into the hardware that, you know, do some of this stuff. Um, SLMs, you've been working on a little bit longer as, LLMs have been popular and like there are modules and the hardware that do that. KV compression is probably newer and maybe that's a software thing not baked into the hardware yet, but maybe some point in the future it's baked into the hardware. The state-based models, that's brand new. You're feeling it out, building the NM systems, learning, and maybe that gets you to a point where you say, oh, we can put this in our software toolkit, or oh, we can put this in the hardware, and it kind of roll. That's kind of how it rolls out. Is that fair?
Yeah, yeah, that's right. Although it's always this ongoing what is worth. We call that hardening, right? When you're going to put things as in hardware support, and you're kind of it's a faith based thing where you're saying we believe this is so important that we're actually gonna it's expensive to put things into hardware, right? So um, we're gonna need to support this, or we believe, and things can change so fast.
Right. So it's like yes, we bet on a transformer that's going to be around for a while. Do we make that same bet on a state space model? And if so, like, which one and what's the right timing for that and that kind of thing.
I can use an example, which is part of what takes time doing encoding for LLMs is the softmax, just the simple softmax function, and you could go so far as to say, well, we believe softmax is so important, we're just going to absolutely accelerate it in hardware. But there are alternatives to softmax, and in fact, the state space are different, and there may be other things coming. So we're faced with this decision of we want to support the existing models as efficiently as we can, but in a flexible enough way that we can adapt, right? Yeah. So even how quantization works has been evolving, and we've been adapting how we design things.
So we've been talking primarily about accommodating LLMs exclusively on the device. Are there approaches that leverage the cloud and the device together?
Yeah. In fact, the way I like to talk about this is, most apps are already apps that are running on your phone are already some combination of some cloud component and what's running on your phone. And it's just the natural thing. You want to utilize the local cloud processing as you can, storage, but there's some things that may be better persistent in the cloud or compute heavy in the cloud or some large database in the cloud. So this definitely will happen as we go forward with these AI models, um, and everything that we're trying to enable models of a certain power and certain functionality that can exist on the edge. Um, but it will work in conjunction with whatever you're trying to achieve in some cloud, in some cloud side as well. And one of the very interesting problems is how to know what to do what where. And so we call this hybrid AI. That's yeah, one of the terms. And it it can be anything as simple as here's my app. It uses the LLM for these functions. It uses you can just pre-decide it uses the local one for these because we know that works. It'll run out the cloud for some of the more maybe planning aspects, or or just more anything that's more difficult. Um, but we are developing methods where that decision can be made on the edge device, based on its own determination of where it effectively the most efficient thing is use the edge device until it needs to go to the cloud, and for the more complex things. So yeah, that's definitely the future for all of this.
That sounds distinctly like where this orchestrator thing that you mentioned earlier might come in.
Exactly. So back to this whole point that we do this edge dead design, and as we've been doing this for a while, what becomes clear is we need to have this capability on the edge device that orchestrates all the different components, and then that can include cloud components. It always will include going going to cloud for information, going to APIs, going to different information sources to that exists out in the world, but also it can go to external large models, AI models in the cloud for when the local model is not sufficient. And it handles the local database, as I was describing, data collection, storage on the local device, all the context, basically all the smarts of what exists on the agent that actually exists on the edge device. So as part of doing that system design, what we is just another good example that of what comes out of it for us, which is this is actually integrated into our chip design, and with the OS, this orchestrator, which is a layer that is gonna provide support to all of our customers that are doing these kind of things. It's like a software product.
I've heard it come up on several occasions, but I wasn't very clear on timing. You said it's going to, so it sounds like it's something that's being developed now as opposed to in people's hands.
Some versions of it are in the hands of various customers. Yeah. I mean, I know the exact state. I should be careful.
So one thing that we haven't talked about that's come up in other research interviews is this whole area of speculative decoding and speculative methods to address some of the bandwidth constraint in particular. Can you give us a recap on that and how that comes into play, and some of the various research efforts that have been supporting that?
Yeah, sure. So as I mentioned, very early on, we all realized, wow, we are so bandwidth limited when we're generating tokens, that whole previous topic. And and given the hardware as is, it's just like, what do we do? And when we jumped in, there had already been a couple of early papers, very recent at that time, on speculative decoding. Because this, that's not just for mobile side. Let me add, even big NVIDIA GPUs have this problem. Um, so and that, but the idea is, well, we have this compute power that we can, as we instead of going through and computing one token at a time for generation, as I was describing, we have the compute sitting there that we could compute all we need for multiple tokens at the same time. So how could we use that? And basically, it's the balance of bandwidth and compute. We're just so way out of whack balance. Can we use compute to reduce the bandwidth requirements? Okay, and that's what speculative decoding does. And it has various forms, but in its most basic form, what you do is you have a draft model. It's a small model that you can run very fast. It's basically trying to mimic what your main, say it's an 8 billion target model in our case. The draft model might be 100 million or something. So and literally token generation is basically proportional to that size. The bigger it is, that's all it takes on a given bandwidth. So it can run literally, might be 100 times faster than the target model. Okay, I should be careful. 10 to 50 is what we would normally do, I should say. Okay, in terms of how much smaller. Okay. Um, anyway, so it can generate. So it's going to have the same input. It's still an LLM. It's just a smaller one, and it can generate tokens. So what you do is you say, okay, why don't you generate a few tokens into the future, and that might be 4, it might be 8, it might even be more in some cases, and then we can actually say, now those are not final generation. You take those and then you're going to run the target model with those as input. And what you're doing is that's kind of an as if. It's like, what if this first token is the next one? What if the first token is the next one? And then what would the next token after that be? And then do that for every one of those tokens. Assume the previous ones are the actual ones, and then compute what you would do for the next one. Okay. What these models do is they create a distribution on the next token selection, a probability distribution. Okay. And then there's a nice statistical argument, rejection sampling, that can, what you can then do is, after the target model does that process, is it can one by one go through and decide which of those are statistically valid. And I won't get into what that means exactly. Okay. But it just means there's a way to do this such that it will accept some number of those tokens and say, okay, I'm going to give the stamp of approval from the target model on those tokens, and I'm going to throw the others out, by the way.
But the idea is that the computation that the target model needs to do on these draft tokens is not the full decode. It's a subset of the decode.
It
And
actually is the full decode. I'll say this. So the target model has this ability to say, given the input so far, Here's a probability distribution over the vocabulary of what the next token is. That's what it does. Okay. And the point here is you can do that exact thing for all 8 input tokens, let's say 8 draft tokens, um, all in one parallel computation, but it's the same thing you would have done. Let's say you pick the 5th token. It's the distribution on that 5th token given the first 4 were the input. Okay, even though they're speculative, these are speculative tokens, but we're saying this is the distribution on the 5th one, as though the first 4 were actually correct.
Or accepted or correct. Yeah.
Yeah.
Got it. Got it.
So that once you do
So is the
accept it,
idea that if the distribution in the fifth one is high enough, you can assume that the first four are good enough?
it's a little more involved than that, and that's the thing. There is a version of that's deterministic, by the way, that just one at a time. Like you don't have to get into the whole rejection sampling statistics.
I'm trying to really understand why, how you're able to skip steps if, ultimately you're doing full decodes.
Right. Oh, here's the point. The whole point hinges on, can I compute these distributions for all 8 tokens in the same amount of time it would have taken me to do it for one token? And when I say compute, the compute is much higher for the 8 tokens. It literally is about 8 times more compute for the 8 tokens than for one token. But the point really is you can do that 8x compute in one
But
pass
without
of
the
the model
bandwidth, without
because the bandwidth is the same.
going back
Yeah,
and forth. Yeah, yeah.
yeah.
Okay,
So
got it.
you're using the excess compute that you have that was just dormant if you didn't do this because it's sitting there waiting for the stupid DRAM to give me the next thing. That's really what happens. Okay. And then there's a whole statistics. So these methods can guarantee that the distribution, like the thing that you're generating, has the same distribution as the original model. That's the key statement. Okay. So there's no approximation going on. It really is generating exactly what the target model would have done.
Meaning there's a way to do the draft and a way to do the rejection sampling that yields a system with this guarantee and better performance relative to uh, tokens per second.
That's right. But even more, let me just disentangle 2 things. How the draft model works does not affect whether whether what you're generating is correct or not.
Oh, really? Like you don't? I would have thought you would need to ensure a certain degree of goodness of the draft model in order for the whole thing to work.
There is a degree of goodness, but it only impacts the token rate, which means
Oh, meaning if it's not good enough, the target model is going to have to generate, do full decodes more.
yes, it's going to reject. They say
Yeah, yeah,
these are
yeah.
bad like that.
Okay.
That's what
Interesting.
you see the point. Yeah,
Yeah,
it is
yeah.
interesting. That's the thing. You get this guarantee that in the worst case, you're just going to go. In fact, in the worst case, you can always accept one token. Okay. And so in the worst case, the only slowdown is how long it took to run the draft model to generate some number of tokens.
But that was wasted compute anyway.
Yeah, but that does cut it because the target model is waiting. You're burning bandwidth. It all comes down to bandwidth in some sense.
Okay.
You're burning bandwidth for the draft model to generate, and that does waste. So the worst case token rate is a little bit lower than what it would have been without this method at all. Okay, but not much lower. But generally, of course, you get as soon as you start getting some hits, then it gets better. Yeah, and so typical gains we say 2x, 2 point something x is typical for these methods, which it's like doubling the bandwidth of your system. It's really quite it became important very quickly.
Yeah. Well, yeah, it's interesting. A couple of things interesting. One is that from the time I first heard about it, which was a conversation with one of your colleagues in research. I think it was Fatih, a year and change, maybe two ago, or a year and a half or so. Like from that time, I've heard it come up, you know, a lot in the intervening time, especially recently. And also, interesting is that, and I think you alluded to this in referencing like NVIDIA GPUs having the same problem. Like it comes up in the context of not mobile, but just high performance LLM inference hardware.
Yeah, any imbalance between bandwidth and compute, as I was describing earlier, this can
Yeah,
benefit it because
yeah,
you can have this excess compute that you try to use in some way.
right.
In fact, I might want to just say at that point, we have a lot of excess compute in our chips, okay, in general, and it compared to bandwidth. And this method I just described, where you're okay, I'm gonna predict some number of tokens into the future. The value of going further and further, well, you're burning this time to run the draft model to generate more tokens, and then for those later tokens to be accepted, all the previous ones have to be accepted, to even have a chance. Then you basically check them sequentially. The third one, the fourth one, and you only go to the next one if the previous ones have all been accepted. Okay. So the point is, and I'm sure it's understandable, that there's diminishing returns on how far you want to how far you want to predict into the future. Okay. So and then we found very quickly is we're still with that sort of baseline speculative, we were not filling our compute. And I'll tell you, you can look at our we have this like teraops. Our chips can support a certain peak rate, a certain teraops peak rate, and then look at the peak bandwidth I was saying is in the tens of gigabytes per second, and there's quite a disconnect there. We have a lot more compute. Okay, and we don't generally use that peak rate. There's other things, but I'm just saying we can support 32. We look at this 64, even in the hundreds of tokens at the same, without, and still be basically bandwidth limited. Okay. And so the sort of predicting 4 tokens or 8 tokens into the future, it is not filling what we can do, what our compute can do. Okay. So it is it was one of our innovations is how, once we see that, okay, what can we do? So then we created a version that we were calling the tree-based. And I will add that, by the way, this has become something very widespread, but it is something that we did early on in all of this development. We do have a paper on it. Okay. Which is, instead of just having one path into the future, very naturally you say, well, I'm going to pick more, just
Just
pick
do it
two
a bunch of
tokens
times. Yeah.
uh, well, okay, actually, there's many possible flavors of this. And one of them was just do multiple. Yeah, you could do it multiple times. Like what you just said. Okay,
Right.
but we found actually even
Or you
better
can
than that.
do, I guess, from tree base, I'm inferring pick a first token and then branch off of the first token and then then branch off of those and branch off of those,
Yes,
that kind of thing.
yes,
Okay.
yes. And then what's interesting is there's actually a few different ways to do the rejection sampling. We actually experimented, or this is literally now just writing out the equations for proving that the distribution is maintained in various ways. And I'll say we had a few ways, but the one we ended up liking we called recursive speculative. Okay, it's recursive rejection sampling. Okay.
And that is the same or different than the tree based?
Well, I would say the tree based is, think of it as generating the tokens in a certain way, and then how we interpret. We use the distributions that were generated and the target distributions to decide which ones are acceptable, which tokens end up being acceptable. And there's a few different ways to do that, and we had to, as I say, so even within the tree based generation methods of doing the rejection sampling, there's a few different ways to do that.
Yeah, I'm envisioning like something analogous to like a binary search or something. Like you have all these leaf nodes and you need to figure out the most efficient way to qualify or disqualify, all of these leaf nodes based on their parents. Something along those lines.
Yeah. So so now let me say the target model now it actually inputs this tree rather than just this linear set of tokens, and it can process. And the tree, our typical tree these days is 32 or 64 tokens, and that we are processing all on one pass of the target model. And so it creates now. There's a lot of what ifs now on each of those paths, and there's distributions created. And given how it was generated, you have to do the statistics, the rejection sampling. Like it just uses the draft model statistics, the target model statistics together to make that to decide which ones to accept to give maximal throughput while still maintaining the original distribution.
Yeah. Very cool.
And maybe one more quick thing to say. Then what we realized is, at first we were doing the simple thing that you said, which is use a branching factor of 2 or 3 or something. Okay. It just is sort of some fixed thing. But then we realized actually you can do likelihood of paths, not just on a per node basis. What you're really doing is generating, like the tree can be like it doesn't have to be like a fixed two
Oh,
two
a
two structure.
symmetrical. Yeah,
Yeah,
yeah.
it can
Okay.
be effectively think of it as pruned in some sense. You're saying, oh, this that pathway.
Pruned during creation, like
Yes,
self pruned
exactly.
or something.
Yeah,
Okay.
that. And then how do you handle that at the target level? Yeah, a lot of things to say there. Yeah, I'll just say something we end up be going back more to the practical side is our hardware does symmetric things nicely, like way GPUs are like this too. And because when you parallelize, well, it's easier if there's some kind of nice symmetry. So there's some interesting trade-offs there from a practical point of view. But yeah, but we called that recursive speculative decoding. And I will add, whatever the cause and effect is here, there's actually a lot of this tree-based speculative decoding out there now, and um, and we continue our developments, and the gains we see. What I said, maybe typically in a realistic scenario, we might see 2x from speculative. We're trying to approach 3x with these methods and see a nice like 50% gain.
Okay.
But it's very much diminishing returns. This conversion of compute into bandwidth is how we think about it. It does not take away the need for more bandwidth in the long run, but it's just one of those. Yeah, it's one of those things that's like on a communications channel. No matter what you're getting from a raw bit rate, throw some coding on, you get some better bit rate. But there's a limit. You still need higher bandwidth eventually.
Are these tree based approaches to speculative decoding kind of the end of that line, at least so far? Or are there other techniques that are being explored? And
There's another whole direction that is still in the speculative family that I think I'll mention quickly. One of the downsides of speculative in general is we were talking about draft models. You have to have this draft model, and you have to create it, you have to train it, however, and that's actually a pretty lengthy process. And then, but that seems to be okay, especially for deployments that have persist. But a real issue is very common these days is you take a large foundation model and you're going to fine tune it, maybe with LoRa parameters or something for specific tasks. Leverage that big model for all sorts of things all at once. And then the issue is, well, this draft model we trained was for maybe it was for the foundation model, or maybe it was for one of the applications. But the problem is, it really just may not work that well for other things you fine tune the model for. And this become now it can be handled by just you can fine tune the draft model, or you can figure out other ways. But we actually have another thing that came out of our lab that we call self-speculative decoding, which is you actually are leveraging the target model rather than having a draft model. You're just augmenting the target model itself in a relatively simple way. And then the target model in the same step that it's verifying previously predicted tokens, it itself is predicting new tokens. So it's sort of self doing. That's what we call it, self-speculative. And what's really nice about this, it does add computational complexity, of course, which we have to some extent. And we can get about a 2x gain from it as well. But its real benefit is, once you've trained it for the target model, then if you fine tune the target model, you don't have to change these parameters. It just will naturally track because of the way it's leveraging the target models to generate them in the first place. So whatever you do to the target model will affect the prediction. And we find that that's actually really robust to the fine tuning. You can add LoRa parameters to the target model, and the pre-trained self-speculative decoding parameters don't have to change, and it still maintains it like a 2x gain. Yeah, and maybe last thing I'll say is, on the speculative stuff is, we definitely are also we are engaged in the research community, and there's quite a bit of effort still ongoing in speculative. And one of the new ideas recently is to leverage embeddings from the target model and still do a kind of draft model prediction. It's like almost like a combination of these two. But and then there's definitely some nice gains. There's still some advancement going on in speculative methods, and how much token rate speed up we can get.
now, one thing that jumps out at me is we've talked about all of this uh, in the context of traditional LLM inference, but now inference is getting even more attention because we're finding ways to use it more to get greater reasoning abilities out of LLMs. I'm thinking about the O1 class models and now DeepSeek R1 and others that apply quote unquote inference scaling to increase model performance. I'm assuming that makes all of the things that we talked about even more important.
Yeah, this is definitely something on our radar, of course. We've had some efforts in these directions, just to study what inference scaling, how it's another way to think about using our excess compute, yeah, to improve the final results. And but I'll say this one way: there's a question of whether how much of this is like it definitely puts a premium on fast token generation. And so all these methods that the bandwidth limits, the speculative methods, that all the things that go into how fast we're actually generating tokens. Because when you do these O1 type methods end up being some kind of tree search with LLM generation. Okay, but it also raises. So if you can just do that generation, and then you have some kind of um, verification model that'll take, okay, let's back up. That wasn't a good direction. We'll search in this other direction. Then how fast you can generate all those, I think of it as like a depth first tree search. You're kind of going down this tree of possibilities. You can generate faster and faster. Okay, with that, then you say, oh, that wasn't good. Let's back up. Let's go this other direction. Um, but it also can be done with parallel generation of the different branches in the tree itself. And by the way, those of us we've had some work in code generation where they do a lot of sampling, beam search, whatever they do in their generation, because um, the model is capable of generating many things, and you have ways of verifying and pruning very nicely in that space. And so here as well, we're going to have some kind of verifier as part of the search process, and so it begs this question of the parallel, like breadth first versus depth first search in a tree, effectively. Okay, and then what interests me, at least in one context here, is well, we have these methods that we're going to burn our compute in order to generate tokens faster. That's speculative, but we can also use that compute just to do true parallel. Like the draft model we're talking about was doing these tree generations, right? You can just pick this tree and have as many paths as you can support. And how that plays out, what is the best way to do this O1 reasoning type stuff in a hardware with our kind of limitations? That's the problem that's really engaging us right now.
And too early to say what that ends up looking like, or are there
Yeah, I'll
ideas
just
in
say
terms
yes.
of what the direction what the direction might
Well, it's not even that the
include? I mean,
methods
it sounds
themselves.
like I mean, I guess you kind of alluded to them. Like one is like doing things speculatively, right? And another is
Yeah,
doing things in parallel, right? So maybe did you already answer my question?
but they trade off. That's the only next step. Okay, is that because we do have fixed. If I burn all my compute power doing speculative, it'll let me go down the tree fast, and I can back up as I need, and that's certainly one mode. But I could have been instead taking some of that compute and generating parallel, search in a parallel sense across the tree rather than straight down the tree. Okay, that I would know. You realize it's not like these methods. First of all, like the Owen methods, we don't know exactly what they are, right? And now DeepSeek we do, and are others, and then there's things that we experiment with. So maybe I back to the theme here, which is this is what we do. We're going to do the system. We're going to understand the system design. However we get there, we're going to do some ourselves. We're going to pull, what we can pull from others' work, but then we have some real questions we're looking at, and then we'll eventually come up with this is what we think is the best way on our hardware, and yeah, we'll propagate.
And these inference scaling reasoning models, the inference scaling is one lens of viewing those models, but there's also kind of a recurring reinforcement learning aspect to the way that they're trained. Does that come up in at inference time, or is that training, only? Does it change anything about the way tokens are generated?
Yeah, it depends. I think you can. It depends how you're verifying and how you're making the decision, the decision making at inference time. And I think the and that but that how you're doing that will definitely play into these decisions of where best to put the compute. That's really the best. What I even, yeah, where we are is that kind of question.
Got it. Got it. Got it. Any additional thoughts in terms of what's next and future directions in this whole space?
There's just definitely going to be development. There's a lot of thinking, as I was saying earlier, on one of our major questions, strategic questions at Qualcomm, is how our hardware is going to evolve, and there's definitely a lot of thinking going on there, um, and trying to try and it try, as I was saying earlier, what it makes sense to sort of dedicate to these kind of use cases, or just the AI problem in general. Yeah, so that definitely will be coming, but it's also more. Um, it's not as concrete as some of these other things. Like, that will take time.
Well, we'll also be including links to the speculative decoding papers and some of the other ones you referenced in the conversation. But thanks so much for taking the time to run through all this. Like, it had a bunch of conversations with folks there and elsewhere about a lot of these things, and I think kind of running through it from top to bottom helped fill some gaps for me. So hopefully that's the case for folks listening in as well.
All right, thank you. Yeah, very interesting conversation, and yeah, I should say it's a very exciting time. Maybe we all know.
Yeah. Awesome. Thanks so much, Chris.
All right, thank you, Sam.